Hi everybody, this is Eric and here's the quick and dirty on upgrading your smart contracts with the UUPS pattern. So what is the UUPS pattern anyway? UUPS stands for Universal Upgradable Proxy Standard. Let's have an example. Suppose you deploy a smart contract and you make a mistake in it, or you want to change some of the logic because your requirements changed. If you deployed that contract in the first place using the UUPS pattern, you are now able to make those upgrades without changing the address that the users will actually interact with. There's actually several ways to do this, but right now at the time of this recording, UUPS is probably the most common. Now, lucky for us, OpenZeppelin already has some tools and libraries to help us out with this, and we're going to look at a quick example. We can use their contract wizard, and they already have a handy button called UUPS, and if we click that, right now take a look at the contract before we click the button. It's very simple. There's basically nothing in there. We click on UUPS, and look at all that it adds. Also notice, by default, it will include the ownable contract. Note again that it's not ownable. It is ownable upgradable. We're also including an initializable contract. We have something inside our constructor, we have an initialize function, and we have an authorize upgrade function. We'll go over all of this right now. Before we dive into code, let's look at the basic architecture of the UUPS proxy pattern. Essentially, there's two contracts, a proxy and an implementation. The proxy contract has two jobs. It holds the state of the contract in its storage, and it forwards any function calls directly to the implementation contract. So you can see here, obviously this is not a fully fleshed out contract, this is just a picture, but it is minimal. It holds one storage variable, which is the address of the implementation contract, and then it has a fallback function inside of which is a delegate call, which is what forwards any calls to the implementation. The proxy contract cannot be upgraded, and this is the contract that any users will actually interact with. Now the implementation contract, and you can see here we have a variable count that's defined. The implementation contract, this is where we define the storage layout of our contract system, but this is not where the storage is held. Like I just said, the storage and the state actually lives in the proxy contract, but the storage is defined in the implementation contract. Now this is also where we hold all our contract logic, like an update count function or whatever else. And we also have to have an upgrade mechanism. This is what allows us to actually upgrade the contract, and if you don't have this, then you don't have an upgradable contract using the UUPS pattern. But the implementation, this is what we swap out with the new implementation as much as we want, as long as we defined everything properly. Now, sounds simple enough, but there's two major caveats that we need to think about. Number one being the initialization problem, and the other one being storage management. So let's get into some code. What do we have here? We have a boilerplate Foundry project. And everything I'm going to show today, you can copy and paste directly from the link in the description. Now, with a Foundry project, that's going to come default with a counter contract, which we have tweaked, and I'll talk about in a second. We have a remappings.txt file. I won't get into that today. We're going to have a counter version 2 contract, which is what we will upgrade to. And we have a proxy contract, which is what the user will actually interact with. So let's start with the proxy contract. Now, as you can see, all we're doing is importing OpenZeppelin's ERC 1967 proxy contract, which handles most of everything for us. Now, where is that implementation address stored that we keep talking about, and where is that fallback function? Let's start with the implementation address. And you can see all we're really doing is calling a constructor, passing in that implementation address, maybe some data, and that's about it. So you can see here we have a function called implementation, which in turn will get implementation, which will give us a storage slot of the implementation address. Now the reason this is called ERC 1967 proxy, if you remember a moment ago we talked about the storage problem, that's what this solves. So let's take an example. If we have something stored in our implementation contract, say account variable, by default, it's going to want to store it in slot 0. So if we call maybe a get count function on the proxy, and it's going to look, now because we're using delegate call, that means we're using the context of the proxy contract. It will look in storage slot 0 of the proxy contract. But if we defined the implementation address like we do here, that will by default store it in slot 0. Now, there you go. We have a storage collision, and it's going to give us some unpredictable results, which is not what we want. So by following the ERC 1967 standard, what OpenZeppelin will do for us is it will, we are using a piece of storage in a proxy contract for the implementation address, but it's not going to be a storage slot 0, 1, 2, 3, 4, or anything that you might actually use. It's going to use a predefined number, and that storage slot is going to be some very high number that, practically speaking, no smart contract will actually use. So that's how we get around the storage problem for the implementation address. Now, after that, we don't store anything else in here except for what is defined in the implementation contract. So now for the fallback function, as you can see, there's no fallback function defined here. Again, that you're going to have to root through all the includes and the inherited contracts from the OpenZeppelin implementation. But as you can see here in the proxy.sol contract, which we're importing here, there is, some fallback logic. And ultimately, that's going to come in here where we're actually making our delegate call inside the assembly block. So that is the proxy contract in a nutshell. Again, this has one storage variable, but it's stored in a place where, practically speaking, we're not going to collide with it no matter what we do in our implementation contract. And we're using delegate call to use the state in the context of our proxy contract, but we can use the logic of the implementation contracts. So there you have it. Now let's look into the implementation contracts. Let's go over the actual implementation contract, which in our case is our counter contract that came with our boilerplate Foundry project. You can see I tweaked it, but the boilerplate stuff is our public uint 256 number variable. We have our set number function, which allows us to set this to whatever we want. And we have our increment function, which allows us to increment it by 1. Everything else you see here is in service of making this upgradable. Now, let's talk about the initialization issue. The basic rule of thumb, don't use constructors. Instead, we use initialize function. Let's go over an example. So let's say we have in our constructor, like in a normal contract, you would set an initialization here. Maybe you want to set number to 10 upon contract construction. But in our case, because we're using delegate call to access everything, what this will do is only update the number in the storage of our counter contract, which is not what we want. We want to update the number in the storage of our proxy contract. So we don't do this in the constructor. Instead, we do it here in the initialize function, which will get called from the proxy contract. This way, because we're using delegate call, this will update the storage of the proxy contract, which is what we want. So again, no more using constructors with the UUPS pattern. Instead, we use an initialize function. Now, you can see here, we're calling two other things, ownable init and UUPS upgradable init. You can also see here, we're importing ownable upgradable. Now, we want this contract to be ownable because you don't want just anybody upgrading your contracts because they can upgrade some malicious code. And because of our initialization issue, if ownable has a constructor, we can't call that constructor either for the same reason I just described. So we have to call its init function, which is called ownable init. Again, for our UUPS upgradable contract, it's not UUPS.sol, it's UUPS upgradable.sol. We can't call their constructor either. We have to call its init function, which is again here, UUPS upgradable init. So we have to do this all the way up the chain for everything we inherit. And again, no constructor, only initialize. And that means these contracts need to be rewritten to have an initialized function. We can't just, we can't import the normal Open Zeppelin ownable contract. So that's what that's about. And lastly, oh yeah, and yes, I can see here in the constructor we are calling something called disable initializers. This is a security measure that Open Zeppelin takes to disallow bad actors from doing anything malicious. And we won't get too into that. This is not a deep dive. This is a quick and dirty description to help you get up and running pretty quickly. And lastly, let's go over our authorize upgrade function. Again, we want this to be ownable, so only owner can call this. You don't want just anybody calling this. This is what actually has an upgrade. So suppose we decide, hey, I no longer want increment by 1, I want it to increment by 5. So I write that in our counter version 2 contract. We see here, we're incrementing number by 5. And what we have to do is deploy this contract, call authorize upgrade, pass in the address of that new deployment. And because we're doing this via the proxy function, this will not affect the storage of our counter contract. It will upgrade the storage in our proxy contract. And if you remember, we're not using storage slot 0. Open Zeppelin wrote authorize upgrade to make sure that the same storage slot we were using before, which is some astronomical number, that's the same storage slot that we're passing in this new address to. And that is the basics of this contract. Now, if you notice one more thing, here in version 2, we have a modifier called reinitializer. We're passing in the number 2, whereas in version 1, we're calling initializer. We only use initializer because this is the first time we're calling it. This is version 1. Everything else, we're going to, any future upgrades, we call reinitializer and pass in the version. So this will be version 2. And this way on a Block Explorer, we can find out any contract we're using, what version we are. Now let's get into actually testing this. So finally, let's test this puppy. So let's look here in our setup function inside of our test suite here. We're deploying our counter contract. We're deploying our proxy contract, and we're passing in the address of our counter contract. And now we're calling via the proxy. We're calling the initialize function of the counter contract, and we're calling the set number function, setting it to 5. Again, via proxy, calling set number of our counter contract. Now here we're testing that all was deployed properly. Again, we're grabbing the number, calling via the proxy contract, which will look at the counter contract. We're calling our number getter function, and here we're checking to see that is it in fact equal to 5, which it should be. Now we test our initialize function via the proxy contract. We call our counter version 1 contract, and we're getting the owner, and we're checking here that it is not equal to 0, meaning that when we called the initialize function, the ownable contract got initialized, and in fact an owner was passed and is no longer the 0 address, which it would be if things didn't work properly. Again, we're testing our increment function before the upgrade, making sure it's incrementing by 1. So we already set it to 5. Now here, if we call via the proxy contract again, we call the increment function on the counter contract. We grab that number. It should now be equal to 6. And lastly, we're going to test the actual upgrade logic, where what we do is we deploy our counter version 2 contract, and via the proxy, we call upgrade to and call on the counter version 1 contract, passing in the address of the counter version 2 contract, making sure it succeeds. Again, we call initialize on it. We call set number. Again, we're going to set it to 5. But now this time, when we call increment, what was 5 should now be 10. Let's go ahead and run these tests. Call forge test. everything passes. So that's all, folks. This is supposed to be a paint by the numbers, quick and dirty guide to get you up and running quickly. And you can, in fact, copy paste my code from follow along what I did here, look at the article, and you can write yourself an upgradable contract. Obviously, you have to tweak it for your own ends. But please read the documentation, get any contract you deploy to the mainnet. If it involves a lot of money, make sure you get it audited. This is not audits for security, but this is good enough to get you started. My name is Eric. I hope this was helpful, and we'll see you next time.